I have the great pleasure to introduce Sam Spaulding. Sam Spaulding is a final year PhD student in the Personal Robots group at MIT Media Lab, advised by Cynthia Breazeal, and his thesis research has focused on developing and evaluating the underlying technologies for interactive AI learning companions to support early stage language and literacy skills, synthesizing in science for machine learning, affective and educational sciences, and interactive media. His research has been published and presented at international conferences, including AAAI, AAMAS, HRI, and CogSci, and has been recognized by an NSF Graduate Research Fellowship, a Human Robot Interaction Pioneers Award, and research grants from the Mellon Fund and Sigma 11 Scientific Society. Outside of school and work, Sam is a big fan of trivia, books, and outdoor activities. I now let Sam start his talk, and thanks a lot everyone for being here today.
Okay, great. Hi, thanks for that introduction, and I hope everyone can hear me okay. I'll start sharing my slides. All right, so it's great to see so many familiar and friendly faces. It was great to see many of you also at the at HRI last week, and some of you even at the workshop that we organized on lifelong learning and long-term personalization in HRI. So thank you all for tuning in there and here, and we'll, my talk will share a lot of common themes with the content of that workshop. And so I hope for anyone who's interested in that topic and following along, you find it really interesting and exciting. I want to talk a little bit about the sort of vision of social robot learning companions, right? And what that looks like, and what do we mean when we talk about the use of social robots in education? As the poll alluded to, there's several different views of what the, let's say, proper role of social robots in education should be, but this is, what I have been trying to work towards, right? A personalized learning companion that combines aspects of being a teacher, like Miss Frizzle from the Magic School Bus, who's like teeing up and structuring and scaffolding learning experiences for you. Someone like Jiminy Cricket from Pinocchio, who's like your sidekick, your buddy. He's like, someone who can offer advice to you, but also hear your ideas and sort of act as a sounding board. Someone who's, framed not necessarily as knowing more than you, but just having a different perspective. And then like Eve from WALL-E is, like a cool and alluring and very data efficient, savvy tool. So someone who can, connect you to the broader digital ecosystem and digital infrastructure. So aspects of all of these three things, sitting at the nexus of that is what we think of when we think of personalized learning companions. So this talk will unfold in two main parts. I think the first part is about social robots as language learning companions in particular. So why is this an application area that's getting a lot of attention? And where are social robots showing a lot of promise in helping students learn? And we'll go over some evidence from educational and linguistic neuroscience as well that suggests that social robots really might have a strong advantage in this domain over other kinds of digital tutoring systems. And then we'll go into a deep dive on a specific project for my PhD thesis, which is about developing personalized models of students that are transferable across different game tasks. And some evidence that this kind of multitask personalization can actually be really helpful from the perspective of data efficiency, and also leads the way, hopefully, towards a more flexible and effective methodology for designing social robot language companions. So In my thesis research, like I said, I've been focusing on developing social robots that are learning companions for early language and literacy skills. And it is an unfortunate fact that here in America, we are quite literally failing our nation's readers. There's a report issued every 2 years called the NAEP, which is often called the nation's report card. And their biannual data, this is from before the pandemic, mind you, showed that reading proficiency in 4th and 8th grade were down again. And that's continuing a trend that's been pretty consistent over the past decade. So reading and literacy they're just incredibly important to all kinds of future academic success. And so the fact that our youngest students are already falling behind in literacy skills is actually an issue of major societal importance. And I think one of the key things to understand about literacy here is that it's fundamentally can be viewed as a technological problem. And what I mean by that is that unlike oral or spoken language, literacy reading is not an innate skill. Right? A neurotypical child will learn to speak if exposed to enough language, but will not automatically learn to read if presented with text and books. So in that sense, there's a technology gap in teaching literacy skills. And one of the key insights from the psychology of learning, and in particular the psychology of literacy, is that what we think of as reading is really more like a constellation of different skills that all kind of work together in concert during the act that we know as reading, right? So we think there's a nice role here for social robots to help children develop, practice, and refine these skills. One of the things we also know is that from educational neuropsychology that learning in general, and especially language skill development, is closely tied to a number of distinct brain regions, especially those regions associated with social and affective processing. So language learning is what they call socially gated, right? Interaction with other agents is actually a critical part of the learning and retention and consolidation phase, right? So I think a lot of people, sort of intuitively understand that when you're interacting with another agent in the use of language, right? When you're actually, saying a sentence and trying to translate thoughts and follow, along in a structured dialogue with another agent, that's actually qualitatively different from doing something like flashcards or fill in the blank exercises, or some of the other common types of exercises that you might see in digital language learning tutors. And then I briefly want to highlight a particularly topical component of this. COVID has really clearly exacerbated inequality in schooling. And people, I think, now are really vividly confronted now with the importance of schools and what they represent, right? Schools they're so much more than just a place where students go to be exposed to information. That's sort of the cognitive only view of what a school is. But schools are also a place where students receive long-term personalized one-on-one attention. And that's based on a long-term relationship. It's a place where students can interact with their peers to repeat and reinforce skills. So it's social in that way. And it's a place where the physical design of the space complements the educational goals and material. So it's also an embodied space, right? So when we think about these extra, qualities that a school brings to the table above and beyond the information, right? Personalized attention, social interaction, and embodied space. These are the kinds of qualities that social robots also bring to the table above and beyond other kinds of digital tutors. So we really think that there's a nice niche here for social robots to kind of fill this gap and address this technological need. So the most relevant body of research to all of this work is what you might loosely call robot-assisted language learning. There's been serious work on this topic now for 15 years or so, starting from early attempts that were really little more than just trying to figure out how students will respond to a robot that tries to talk to them, And all the way up to now, we are, as a field, capable of doing pre-registered, like multi-month, large-scale studies with hundreds of students. So it's not quite at the scale of nationwide educational assessment research, but it is a really an attempt at which we can really start to draw some substantial conclusions about how well this technology works. And so the conclusion, from this sort of landmark summary of a lot of the field that was published in 2018 is that social robots have been effective at increasing cognitive and affective outcomes similar to those of human tutoring on restricted tasks. And what are those restricted tasks? They're short, well-defined lessons delivered with limited adaptation to individual learners or flexibility in curriculum. So these results from these kinds of, largely single session tutoring interactions with limited personalization, generally they paint a picture of benefits that social robots can deliver that are stable, positive, and modest. So where is the field going from here? What are researchers looking towards as kind of like the next thing over the horizon? I think researchers are looking a lot more towards educational interactions where personalization plays a big role, a much larger role than in some of these smaller scale studies, and also to long-term interactions that unfold over different tasks and over different environments as a way of developing more richly personalized models. So don't worry, I'll walk through each of the boxes in this diagram in turn. This is just kind of the roadmap to sort of, let you know where we're headed. So starting at the top, personalized student modeling helps promote student learning and engagement. And I think this is, a very active research area. There are a lot of people who have studied this from a bunch of different angles, right? But a lot of the past research shows it's beneficial for social robots and intelligent tutors in general to personalize their interactions with students. So to learn a model from interaction data about what parts of the curricular task a student knows or doesn't know, and then adapt the interaction to help boost learning and engagement. So this is often, operationalized in the form of content personalization, right? Adapting the content or adapting what task a student is asked to do. And that's, it's called the flow state, the zone of proximal development. It's known by a lot of different terms across different fields, but the basic idea, I think, is one that everyone can sort of intuitively appreciate, which is that if a task's difficulty, vastly outweighs a student's ability, it's not going to be a successful learning experience because the student's not going to know where to start. They're not going to have any way of really getting a hold on that task. And likewise, if the task's difficulty or the student's ability vastly outweighs the difficulty of the task, you'll often see students getting bored or not wanting to pay attention or just sort of, losing interest. And that's also not a particularly effective form of educational learning experience. So the key challenge here is keeping students in this, this sweet spot of optimal challenge. And what the digital tutors can do is they can modulate the task difficulty, right? They can decide, okay, what content is coming out next. So to keep the students in that zone of proximal development and that optimal challenge space, you need to be able to accurately estimate student ability. Now, in order to learn a personalized model, that requires interaction training data. And I think almost anyone who has tried to do, interactive machine learning in a human-robot interaction scenario can appreciate that data is a huge challenge for people who do this kind of work. And there's, it's often very difficult to get enough data to really train, a good personalized model from, a single interaction. And so what researchers have kind of been doing to get around this is saying, okay, let's do long-term interaction. We're going to do multiple sessions. We're going to collect a lot of data from each session, right? So you have studies like this one, which we conducted at Boston and Cambridge public schools, where students are interacting with the robot, once a week or twice a week for, let's say, 6 to 8 sessions, right? And as the the students, go through each session, the model is updating and, repersonalizing with data from the previous session. And so these actually work, pretty well. This is sort of like the most, I would say these are, some of the strongest results we see in terms of the effect of personalization on learning in HRI scenarios, right? Students are learning over the course of the interaction, and that learning is significantly driven by the personalization in the model, right? What we also see from studies like this, though, is, we also see that there's kind of a limit to how far you can get with a single task, right? So in this study, by the 6th or 7th session, students were already realizing that this is, it's going to be the same task every time, right? And they were picking up on little patterns in the robot's behavior. They were picking up on specific catchphrases. They were losing engagement in the, doing the structure of the interaction again. And, you can see as engagement drops off, shortly after that, there's also a drop off in learning. We kind of, after we wrapped this project up, we sort of, went back to the drawing board and we're thinking, all right, well, what can we, what can we do to take this to the next level, really, right? And specifically for literacy learning, we knew that a single task doesn't really show the whole picture, right? Mixing things up with different contexts, different skills, different usages of words, that's what the sort of science of reading, would suggest is going to be a more engaging and effective structure for a long-term kind of interaction. So that led us to thinking a little bit more about this idea of multitask personalization and transfer learning as the sort of computational basis for that, right? So the idea of multitask personalization is that you can combine data from students' interactions in multiple different educational tasks, and that could keep students engaged and learning new types of student models over the course of a long-term interaction, while still personalizing those models using data from all the tasks and all the sessions. So our primary approach to doing that is going to be through transfer learning. And transfer learning is an area where there's been some, a lot of really exciting improvements lately in robotics for physical tasks, in natural language processing for, sort of generalizable models that can then be fine-tuned on things. But the key idea of transfer learning is that you can train a model on data from multiple tasks or multiple variations of a task. And it's not the same as just making sure that you have varied data in your training set, right, to reduce your generalization error. The key to transfer learning is recognizing that your training data can come from different source tasks, what we call source tasks, and that the differences between tasks can be quantified in some way. And so by accounting for the differences in those source tasks and modifying or adjusting how you treat certain data in the training process, you could end up with a better, or more flexible, or more efficient model for a target task. So we see a number of potential benefits for this paradigm of student modeling. Obviously, being able to assess different skills and get that sort of more holistic picture of student knowledge is one, but also, avoiding the cold start learning problem, right, where you have an interactive, machine learning system, but if it performs poorly in its, sort of initial state, users aren't going to want to participate in, they're not going to want to interact with it because it's sort of flailing around in this early stage. And so it's not getting good data, sort of gets choked off early because of a lack of high quality interaction data. We also think that it has benefits for user engagement and also data efficiency in model learning. So I think I'm just, in the interest of time, going to skip over some of the continual learning bits here and just jump ahead to the main project that kind of demonstrates the use of this multitask personalization and transfer learning method. So over the years in personal robots, we've developed this sort of multi-use deployable system capable of supporting different game interactions with Jibo the robot. So students are typically playing a game face-to-face with Jibo, and he's getting sensor data from a number of different channels. He's got cameras in the head, and there's also a fixed camera in the station. There's microphones for speech data, and it's all synchronized with the game actions that both the student and the robot are taking in the tablet game. And so specifically, I'm going to talk about two different literacy games here, which are going to be the two different tasks that we are trying to transfer models between. So each game task is designed to support and assess a different kind of literacy skill. And within each game task, the robot is interactively learning a personalized cognitive model of the student's mastery of that skill. So a lot of this was, sort of the prelude was talking about kids and young readers, and that's really the audience that a lot of the early work in this project focused on, and that's the system and the games were originally designed for this population. With COVID, our ability to work with those students and partner with a lot of our school and summer camp institutions became a lot more difficult. So about 9 months ago or so, we totally redesigned the games to be geared a little bit more towards a population that we could work with more easily, MIT undergraduates. So the focus of these games is now not really so much on early reading and literacy, but on second language learning and on teaching MIT students a little bit about the Russian language and the Russian alphabet. Russian, as it happens, has a number of nice properties for second language learning. It preserves some of the multitask complexity of early literacy for early readers. You have to learn new symbols, new sounds, how they map to each other. Roughly, you can sort of divide the letters in the alphabet up into 4 main groups. So you have some letters that have roughly the same shape as their Latin counterpart, and they make roughly the same sound. So that's fairly easy. You've got some letters that have, a familiar shape, but they make a different sound. So that's something you've got to correct for. And then, the other flip side of that is that you've got letters that look novel. They have a new or unfamiliar shape, but they actually make a familiar sound. And then the hardest of all are these letters all the way on the right that have an unfamiliar symbol, and they also make an unfamiliar sound. It's not a sound that is, sort of naturally maps onto a single letter in English. So students, just as early readers do, they bring some partial knowledge to the task, but not a lot. There's still, quite a bit of learning that needs to happen. So the first game I want to introduce to you all is called Word Decoder. And in this game, the tablet shows transliterations of common English words up at the top. And then there will be different options. So those are English words that are spelled out using Russian letters. And then students have to pick from a list of pictures at the bottom, which one best is represented by that word. So I'll play a little video clip of some gameplay, and you'll see how Jibo and the student play alongside each other, play this game, taking turns and sort of interacting in the educational play.
Oh. Hi, and welcome to Word Decoder. We're going to learn how different letters sound in the Russian alphabet, using familiar English words. Do you need to hear the rules?
No. Sure.
I guess the first letter makes the SH sound.
Synth.
This is a really cool game.
So the robot is actually coordinating a lot of things behind the scene, even though it's framed as this co-playing peer, right? In actuality, Jibo is basically structuring the entire game. At the start of each round, Jibo decides whether to do the observe action or the demonstrate action. So when demonstrating, you saw that one first, right? Jibo rings in first and gives an answer and basically teaches a little lesson, right? Gives a hint or a clue about some aspect of the curriculum. And when the robot sits back and observes, chooses the observe action at the start of each round, that's the robot's way of getting more information about the student model, saying, hey, I need to learn more about what the student knows or doesn't know. So here's an opportunity for me to sit back and get some more interactive data. After selecting, one of those two objectives, we call it, the robot is also using what's called a content model, right? Deciding, okay, which word, which actual piece of content will sort of best serve the goal of this objective, right? And so using an active learning protocol, Jibo can actually pick, in the case of the observe objective, right? We'll pick the word that the model has the most uncertainty about, or in the case of the demonstrate objective, pick the word that the model is actually quite certain the student does not know, right? And I'll go a little bit more into how exactly that's computed later on. We dive deeper into the cognitive model. So the next game I want to introduce is called Word Builder. This is the second game of the two. And Word Builder is a slightly more complex game. So in this game, students will hear full-on pronunciations of Russian words at the start of each round. And then they'll also see that word spelled out using letter blocks in the center. And the game will spell out all of the letters except for the first letter. So the student and Jibo's job is to use their understanding of Russian sounds and letters, right? The correspondence between sounds and letters, and also that spoken pronunciation clue to correctly fill in the starting letter.
Pavlin. A new word. Let's figure out the starting letter. I'm pretty sure this is the right letter. That one was tricky.
Nice one.
Изогнутый. A new word. Let's figure out the starting letter.
Изогнутый.
Good job, partner.
Блок.
Do you know what the starting sound is? I can solve this one. It's similar to English.
Блок.
What letter does this word start with? Good job, partner.
Тюрьма.
Okay, so both of the games are backed by a Gaussian process cognitive model. And so this is a model that's trying to estimate a student's mastery of a particular skill applied to each word that could come up in the game. So a very quick introduction to Gaussian processes and why we think they're a good tool for modeling this kind of interactions. All you really need to know about Gaussian processes are they're a class of supervised learning model. So they take in some training points and then they make Gaussian predictions over a set of test points. So that means the predictions take the form of a mean and a variance. So here in sort of the canonical example of a Gaussian process, you can see these 5 blue dots. Those are the training points. And then the dashed red line, that's the Gaussian process posterior mean. So that's sort of the mean estimate taking into account all of the training points, right? And then the gray shaded area represents the variance around that mean. So what you can notice here is that close to the training points, the variance is sort of, tighter, right? The training points like rein in the variance. And then the further away you get from those training points, the wider the variance, the more the uncertainty is around that mean estimate. And I'll just point out that distance is based on the covariance function, which is kind of the primary parameter that's driving the inference of the Gaussian process model. Now, in our case, our domain is not over numbers like that previous graph, but it's actually over words in a word space. So you can think of each of the words in our curriculum, which is the set of all the words that can come up in the game. There's a point estimate there, right? So this is what the graph of the Gaussian process prior looks like, and each little Gaussian here is an estimate at a point in word space, right? So starting at the top, that's sad, mad, dad, plaid, right? These are all the words that can come up in the various games. So Gaussian processes, they have a number of nice properties, especially for our use case. They do really well with small data. They generalize well to points near the training set. the covariance function that I mentioned really drives forward most of the inference. And that's great because that allows us to encode some of the domain knowledge that we have, right? It's how we kind of make the model inference match up with our understanding of the dynamics of learning in these kinds of scenarios. This is the equations for the two covariance kernels for our games, but the primary thing to point out here is that in word decoder, what's really driving the covariance is this bonus term that brings words closer if they share a rhyme ending. So words like shell and well, right? And fundamentally what that means is, it's a clue to the sound of the word. And so it's, kind of an indicator that if you can or you can't solve one of those words, you're more likely to be able to solve or not solve the other one, right? Your responses to those two words are likely to be highly correlated. And in Word Builder, there's a bonus for words that start with the same letter. So words like pavlin and papa, right? The task is to be able to identify the starting sound. So if you can identify the starting sound for one word that has that same sound, you're more likely to be able to do that to the other word as well. So this is the plate notation graphical model laid out that kind of shows all the data and how it's flowing and stuff. I think in the interest of time, I'll just skip on to a working example, but it's useful to have if people have questions later, we can refer back to it. So this is what the Gaussian process prior looks like. We have no prior information, and the estimates for every word are sort of a nice, smooth, high variance Gaussian centered around 0. And then in a case like this, where the student, let's say they answer, the correct solution here is jog, right? So let's say they get this one right. What happens to the model? The estimate for jog shifts highly positive, and the variance gets, tighter around that because that's a directly observed demonstration, right? That tells us something that's like a training point for the rest of the model. But you can also see that all the other estimates at the other words in the curriculum shift around as well, right? The closest ones are going to be the ones that are closest according to the covariance kernel. So frog, dog, log, right? Those all shift, heavily positive, and their variance tightens up a little as well. But all the other words in the curriculum are affected by that training point, right? You can think of it as like gravity in the solar system. Like everything affects everything else. They're all connected, but the strength of that connection is based on how covariance close they are to each other. So after a bunch of different demonstrations, right, after several rounds of this is sort of what the posterior model might look at. You can see some words there's been positive demonstrations, some words there's been negative demonstrations, but even the words where there hasn't been a directly observed data point for that word, based on all the other points and how they affect the Gaussian process inference, we can still get a pretty good estimate of how likely a student is to be able to correctly answer or not answer that word. So this is happening in both games as the gameplay unfolds, but the key thing we were interested in is how can we transfer data across these games? How can we take a model from one game and use that to learn a better model in the second game, right? So the naive approach would be, hey, what if we just took all the data from the first game and we just used it to add in the model and start off the model in the target game off with more data, right? That's okay as long as the tasks are highly correlated, right? A more sophisticated approach is what we call instance weighting. And so that's where we sort of look at each data point in the source task, and we basically assign it what's called a transfer coefficient, right? And that transfer coefficient for each data point is going to be based on how similar the role of that word is in the source and target tasks to inference, right? And so I think what's helpful in kind of understanding this concept is looking at sort of the ideal case, which in this case would be looking at the green the green example, right? So let's say in the black, this is our source task instance. It's a demonstration of dog, and dog has covariances to various distances, right, to all of these other words. In the ideal case, in the target task, right, if the word dog has the exact same covariances to all the other words in the curriculum, then functionally it plays the same role in inference in that target task, right? A positive demonstration of dog in the source task, would have the exact same effect as a positive demonstration of dog in the target task if they have the same covariances to all the other words. So in that ideal case, when the covariances exactly match, the transfer coefficient is going to be 1. That's not the case. That's almost never the case, right? That's sort of like an ideal case, just to illustrate the point. Much more often it looks like this red situation, right? Where the covariances are different, and they're, you sort of have to figure out, all right, well, how different are they? And you sort of take the average difference between dog and every other word across these two tasks, and you sum that up and you do a little normalization, and that's how you get the transfer coefficient. So our transfer process is, looking at all the data from one game and doing this instance weighting procedure based on how similar the role of that word is between the two tasks. So I'll just quickly cover some of our evaluation here, and that's we've been running a human subject study with 4 sessions, and I'll just talk about personalization groups A and B here. So these are the exact same technological setup, right? The exact same computational modeling setup. The only difference is the order in which they play the 2 tasks. So you can see here that in group A, in session 1, they're playing word decoder, and in group B, they're playing word builder, right? And this allows us to really do a nice comparison where we can really isolate the effect of transferred in data on the model performance. So, the only difference between group A session 1 and group B session 2 is that in group B session 2, you're transferring in 1 round of word builder data from the previous session, right? And vice versa. So looking across, we can do this sort of staggered comparison across the groups and really get a sense of, hey, how much is the transferred in data from previous sessions affecting the model prediction performance? So there's 3 main questions that we're interested in, sort of probing here with this comparison. The first one is just viability of transfer, right? And this is, sort of the kind of baseline evaluation for transfer learning projects. You want to make sure that the tasks are actually close enough or related enough that it's feasible to do transfer learning. Not all tasks work right in concert together for transfer learning. So negative transfer is the idea that if the tasks are so far apart that bringing in data from the source task could sort of like poison the model for the target task. So you really want to make sure that that's not happening, because otherwise you're just, it's hopeless, right? You'll never get it off the ground. The second question we're interested in is the efficiency, right, of multitask model performance. How does transferring in data affect the learning curve of a target task model? And what does that look like at various checkpoints throughout the learning phase, right? And then we're also interested in student learning. Fundamentally, at the end of the day, we need to make sure that these systems are having the intended effect on users that we hope they are, right? Are students learning? Do they appear engaged? Is it effectively, helping them master the material? So here are some preliminary results. I think this is about half the data. I need to go back and update this when I get a chance. But on the left, you can see condition A with the solid line and condition B with the dashed line, right? And this is over the 4 different sessions. And on the y-axis, this is model prediction accuracy. So at various checkpoints, the model is trying to predict the next n data points, right? This is what's called a walk forward analysis, where you're training on some of the data that you've seen, and you hold out the most recent data as a test set. And then as you sort of progress along the interaction, you're always kind of, you're adding the last test set into the training data, and then the new data that you've just now seen, right, gets set aside as the new test set. So that's why these the last 2 sessions only have 3 checkpoints, right, instead of 5, is because at some point you run out of new data. You've stopped collecting data, and so the final data that you collect will just only be a test set, never a training set. So this is kind of the critical comparison that we're most interested in looking at, right? This is, how does the transferred in data affect model performance, right? And so you can see here in Word Decoder, there's a really substantial effect. Transferring in data boosts model performance by about 10 percentage points, which is a pretty big jump in model performance. And we can see that this is especially pronounced in those early phases of training. So that's exactly what we were sort of expecting to see with the cold start learning problem. I will just note that the results are not quite as clear cut going the other way, right? Word Builder, there's some improvement, but not really much. It's not very clear. So I think there's sort of an open question as to why transfer is so much more effective going from one task to the other, but that is not necessarily reflected going the other way. Looking at student learning results, these are across the 4 different experimental conditions, and gray is what you would expect from chance. This is a post-test assessment for both word learning, Russian vocabulary word learning, and also letter sound mapping. And we can see that, yeah, students are definitely learning. So the interaction is successful at helping students learn. So recapping these results here, and I'll just come to leave you with a few closing thoughts here, because I know we want to have some time for questions and discussion. But I think if I leave you with anything, it's that language learning fundamentally is a task that requires engaging students along cognitive, social, and affective dimensions. And that social robots, I think, are really great at tapping into all of those things. But that personalization, and specifically personalization across different tasks, I think is really sort of the next frontier for making these systems really engaging and really helping them be able to deliver on what I see as just the tremendous potential they have to have a real impact in this very important societal challenge. So with that, I will turn it back over to Sylvia and Miguel, and I'm happy to take any questions that people might have.
Thanks a lot for the talk. It was super interesting, really, thanks a lot. I'll now ask if you have any question. There are a lot of clapping hands, you can see. That's great. Do you have any question? Yes, there is one question. Please go ahead, Baha.
Well, I can start us off. Great talk, Sam, as usual. And I was wondering, so since you both work with both children and adults, what do you see as the differences in terms of personalization, in terms of the interaction experiences, and what would be your suggestions for the both groups?
Yeah, I mean, there's huge differences, both in terms of, I'd say the sort of like perceptual data that we get in is very different, sort of patterns of game interaction are very different. But I think the biggest difference is in the interaction design. These games, they went through several rounds of gameplay testing and design, and always the feedback we were getting when we were targeting younger students was, you got to simplify the interface, right? Simplify it, make it a very simple game. It can basically just has to be like tap to touch, and there can't be any, this is one, right? There can't be any text on the interface. It has to be like green check or red X, because they can't, they can't reliably like read or navigate a menu. So one of the things that I'm really excited about, potentially seeing this work extended to, is to more complicated linguistic tasks, right? Not just sort of, phonics and letter matching activities, but maybe even things like sentence construction or narrative construction, and seeing how these kinds of personalized modeling interactions could be extended to more complex linguistic skills with, slightly older populations that can sustain that sort of interaction.
Great. And did you see any differences in terms of engagement?
In terms of engagement, I mean, it's kids are a lot more varied, I would say, in terms of their reaction and responses to the robots. I think, MIT undergrads are a very atypical population in some ways, in that they're pretty nonplussed by the robot. They're like, yeah, okay, a robot, I've seen these, like, whereas kids, of course, are surprised and delighted by all kinds of things all the time. So I think, understanding your population and trying to design an interaction that, helps them, yeah, I guess like get involved in the activity to the extent that your model or agent or plan is for them is pretty important when you're trying to like do things like a controlled randomized study, right? I mean, there's sort of a different approach, which is like we're gonna give this artifact to different populations and see how they react to it, and that is going to be kind of the research in and of itself. But if you're trying to do something that's like a little more controlled, or you're trying to find learning differences or things like that, you want to make sure that the interaction is kind of unfolding, or that you're measuring what you think you're measuring, right? That it's unfolding the way that you think it should.
Wonderful, thank you.
Okay, Marina, if you want to ask your question, please go ahead.
Awesome, great talk. I'm very curious about the sort of role, based on your experience, of nonverbal communication in these types of interactions. And so the first thing that I thought, sort of watching the video that you showed of Jibo, is that Jibo was turning towards sort of the screen area, but it didn't quite have eyes. So it didn't, like, for me as a watcher, as a third person, from a third person perspective, it didn't look like Jibo was actually looking at this screen. And so I was curious, because you've used robots before that have more clear eyes. Would it have been helpful to sort of have that additional communication modality from the robot's perspective? And sort of vice versa, right? Thinking about the users, were you using in an interesting way their nonverbal reactions to what was going on?
Yeah. So I think nonverbal interactions are pretty, I think, like under, let's say, utilized in personalization models. I think there's still like very much an open question of, how do we integrate sensed nonverbal data, right? Like facial affect or body pose or gross movement or things like that. How do we factor that into these sort of more well understood cognitive models, right? Where we kind of know, okay, a right answer, a wrong answer, like we can factor all of that information into a model, but it's less clear how nonverbal data can fit into that picture, right? And so that's something that a lot of people are still researching as an open question. Specifically about the robot looking at the tablet and things like that. There were initially there was some confusion about, is the robot taking a turn? Is the robot doing this in the game? And one of the things that we did was, I don't know if it was clear from that video, but we've had the robot, whenever it's taking a turn, it lights its light ring up purple, and then we also put a purple border around all the game objects that it's like moving or touching. And we did do some, just sort of like confirmation checks to make sure that people understood that when the robot was doing something in the game and not because of that. But again, that's sort of a kind of an interaction design feature that it took us some time to actually like settle on and make sure that that was happening correctly.
Awesome, thank you.
So we have like 2 minutes for last question if you want. Otherwise, I put a link to the Slack channel, and we created a specific channel for, yeah, we have another question from Andrew. Please, Andrew, go ahead. For extra question, please join the Slack channel so that we can continue to talk about this.
Sam, great to hear what you've been working on. So you said something kind of at the beginning before you got into the meat of your real research that sparked a question in me. So it may not be really the main thrust of what you're looking into, but you mentioned briefly the robot's social role as sort of a peer, and then also sort of behind the scenes, it's coordinating a lot of the other stuff. But I'm wondering if you looked into that sort of factor of the social role of the robot, because it's not like there are multiple choices there, right? You could have it, right. You could really have it as an instructor. You could have it as a tutor, which is like a little different than an instructor, but more sort of like a coach, or you can have it as like a true like player two, right? And I'm wondering if you looked into that, or if you know of other people who looked into to things like that, and what you can say about the effect of social role.
Sure. Yeah, a social role is a really critical aspect of, I think, like having the robot feel authentic, right? It should like have a role that is at least like understandable or like legible to participants, right? In this case, the robot is very clearly framed as like a peer. We're like playing together, and I'm gonna like say some stuff that I know, but Jibo also makes some mistakes occasionally, right? And or like asks questions and is like, I don't know this one. Do you know this one, right? Another researcher in personal robots, Huili Chen, has specifically looked at the impact of robot role on learning and engagement, I think. And I think she had an HRI paper on that a couple years ago. I want to see if I can find it. Yeah. Or I think it's a journal paper here. Let me see if I can drop that in the chat. And I think she did explicitly look at different kinds of roles that the robot could take, like all tutor role, all sort of like younger peer role, like always asking questions and not, offering information, and then sort of like a hybrid model, where I think based on like different interaction contexts, the robot kind of like switches roles. So that I think is a pretty cool project. And as far as I know, I think this idea of like adaptive role switching, if you could get that right, that really feels like the sweet spot for framing of social robots.
Awesome, thank you. I look forward to that paper.
Yeah.
Okay, so thanks a lot once again to Sam for the presentation, for all the questions and the discussion that we had. I will now take last few seconds to introduce the next speaker. So let me share my screen. So our next speaker would be Stefania Druga from the University of Washington, and she will talk about creative coding with AI friends for youth. And the session will be on March 30th. So see you all there in 2 weeks from now. Thanks a lot.